Let's start the next session after the lunch break. This is the CGM session, and we will start with Claude-André Faucher-Giguère with inner CGM virialization and its effect on star formation rate variability, outflows, and the formation of thin disk. You can start when you want.
Thank you very much for the invitation. It's great to see you all in person after so many years. So this is going to be a theoretical presentation about the connection between the physics of the circumgalactic medium and the evolution of the essential galaxy. And specifically, I'm going to talk about recent results on the whole of the virialization of the inner circumgalactic medium on the evolution of the variability of galactic star formation rates, the properties of galactic wings, and the formation of thin disk galaxies. Function of time since a burst of star formation, and the energetics are tied to starburst 90 population model. And on this slide, what I have is a video of one of our simulated Milky Way mass galaxy, and I want to show you this video because the intuition that you can get from it will be very important, or at least useful, to understand some of the quantitative results I'm going to expand on. So what you can see at the top is the gas that's infalling in from a large-scale structure to the center of a dark matter halo that's being tracked. This gas is color-coded by temperature. And you can see at high redshift how the gas distribution is highly clumpy and also highly dynamic. And the radial pulsations that you sometimes see in the cold gas are the simulated equivalent of powerful galactic outflows driven primarily by supernovae. And it's only at relatively late times in these simulations of Milky Way mass galaxy that you are going to see the emergence of a long-lived rotationally supported disk in the gas. Roughly at this time in this particular simulation. And it's out of this thin gaseous disk, viewed roughly face on here, that the thin stellar disk is eventually going to emerge. And this kind of evolution from a highly bursty, highly dynamic state at high redshift to a much more kind of time-steady, rotationally supported configuration is generic in these simulations, at least for Milky Way mass galaxies. And so here you have a late-time merger between a small dwarf galaxy and your bigger L-star type galaxy. And at the end, you have simulated galaxies like this one that are broadly reminiscent of local spirals. So a bit more quantitatively, so these are quantitative plots for the same simulated galaxy as on the previous slide. The top shows you in black star formation rate as a function of time from redshift of 4.5 to redshift of 2, and you can see these spikes that reflect the burstiness of star formation in this early regime. And these bursts of star formation are typically followed by bursts of outflowing gas through the inner, and also the outer, actually, CGM traced by the dashed and dotted red curve here. And at these early times, the gas distribution looks like this, highly clumpy and also highly dynamic. And the same simulated galaxy by low redshift, from redshift of 0.5 to redshift of 0, plotted here, has settled into a quasi-steady state in which the star formation rate is now nearly constant, modulo modest short time scale variability. The outflowing gas has a outflow rate that's much smaller fraction of the star formation rate in particular, and is more reminiscent of a weak galactic fountain than a galactic outflow that reaches far out in the CGM. And at these times, the galaxy looks like this, so a long-lived rotationally supported disk. And next, what I want to make a bit more quantitative is the connection between the burstiness of star formation and the formation of a long-lived thin disk. And so these are plots extracted from a paper led by my graduate student, Alex Gervich. And here the first step is to identify the time at which the star formation rate stops being bursty, so the transition from bursty to time-steady star formation. And it turns out we can do this quite accurately because in the fire simulation, this transition is quite abrupt. It feels kind of like a phase transition, in fact. And so what the panels here show is measures of the star formation rate variability in 3 independent Milky Way mass galaxies that were simulated. And what was done is to shift in time each one of these curves such that they all kind of end the bursty star formation at this delta T of 0 relative to the end of bursty star formation, that the time we labeled T bursty. And if you focus on the bottom panel, this basically says that while you have order of magnitude time fluctuations in the star formation rate at early times, this variability drops by about an order of magnitude in a time span that is less than a gigayear. So this is the sense in which this transition is relatively sharp. Okay? And on this slide here, after shifting these simulations in time such that they all end the bursty star formation at a value of delta T of 0, what we look at is how kind of the properties of the gas and stellar distributions evolve. And I will suggest you focus on the solid curves which correspond to the gas distributions. So the top panel is a measure of the geometric aspect ratio of the gas distribution. So you can see that it evolves from being quasi-spherical, so aspect ratio not much less than unity. And this aspect ratio dropped very significantly around the time of the end of the bursty star formation. In the middle panel, we have a measure of the circularity of the gas orbit. So this is median Jz over Jc, where J is specific angular momentum. And what you can see is that while at early times there is kind of gradual increase in circularity of the gas resolution elements, there's order of magnitude time variability in that, so kind of reflecting the large dynamic fluctuations in the gas at these times. And it's very nearly at the end of bursty star formation that all the gas elements settle onto nearly circular orbits, and the fluctuations have essentially disappeared. And in the bottom panel, we have a more observational measure of the degree of rotational support. So that's V over sigma for the H1 gas. So you can see that at early times we have values of order unity. So a little bit of rotation, but the dispersion is almost as significant. And it's around T bursty that there's a rapid increase in that rotational support. Though again, there is certainly some angular momentum before T bursty, and that might correspond to an earlier formation of a thick disk-like relic that would be observed at later times. But the aspect that I'm going to be focusing on today are ones that change relatively rapidly at T bursty, and that might correspond to the formation of a really thin, long-lived gaseous disk. And what I'm going to propose today is that these transitions at T bursty can, to a large extent, be understood in terms of the physics of the circumgalactic medium, so the gas in dark matter halos. And I will start with a cartoon picture for different physical regimes that the CGM can be in. So cosmologically, when dark matter halos grow, they evolve from a first regime which we might call rapidly cooling, in the sense that the cooling time of the gas is everywhere shorter than a local freefall time. And so in that regime, the gas essentially free falls cold into halos and accretes supersonically onto the central galaxy. And the supersonic accretion, I believe, is important because it means the central galaxy doesn't know that cold streams and cold clumps are coming towards it. So it might be surprised when it gets bombarded by this infalling cold gas. And then as the halos grow, it turns out that the CGM virializes on average from the outside in, meaning that you first develop an envelope of hot gas at the larger radii in halos. But for a while, you still have a supersonic infall at the center, because for kind of generic gas profiles in dark matter halos, the ratio of cooling time to free fall time increases from the inside out. So the inner parts are the last to kind of stably virialize. And so at these intermediate times, from the point of view of the central galaxy, the gas is still crashing onto it supersonically. But eventually, the CGM is going to fully virialize and become filled with hot virial temperature gas, where everywhere the cooling time is longer than the free fall time. In spherical symmetry, we would say the halo is now filled with a cooling flow that slowly feeds the central galaxy. And we think this kind of final phase of CGM virialization is important for galaxy evolution, because this is when, relatively abruptly, the boundary conditions of the central galaxy change. So now the gas is cooling subsonically onto the central galaxy. This is related to what Avishai sometimes calls the golden mass, or the classical transition between cold mode and hot mode accretion. And here, really kind of, we think, is a novel element is the focus on this outside-in direction of virialization, and the fact that when the boundary of the central galaxies change in physical properties is kind of at the very end of that process. Okay, so this was a highly idealized cartoon in spherical symmetry. So this is an illustration of how the CGM virializes in the fire simulation, which are far from spherically symmetric and also much more dynamic. So this shows maps of temperature in the inner circumgalactic medium in the Milky Way mass galaxy from redshift of 1 to redshift of 0. And each panel is further labeled by our indicator of whether the CGM has virialized or not at these inner radii. So that's T cool over T free fall at a tenth of the virial radius. So a tenth of the virial radius is just a little bit outside of the central galaxy. And what you can see is that prior to inner CGM virialization, you have a complex and dynamic mix of cold and hot gas in the inner CGM. At those times, you don't have anything that looks like a long-lived gaseous disk. And as time progresses and the halo grows, the hot gas moves from the outside in until that hot virial temperature gas fills the entire halo down to the boundary of the central galaxy. And at that particular final time, plotted edge on here is a thin, cold gaseous disk. And in the bottom panel, I am plotting corresponding maps of pressure fluctuations. And what you can see is that at these early times, prior to ICV, you have order of magnitude pressure fluctuations from place to place. And we think these pressure fluctuations are important because they include paths of least resistance in the CGM, into which, when you have bursts of supernova feedback, the gas from the central galaxy can easily be ejected out to large radii in kind of CGM-scale galactic winds that repeatedly disperse the galaxy that's trying to form at the center. Whereas when the inner halo becomes filled with virial temperature gas, not only is the kind of mean thermal pressure relatively high, but the fluctuations from place to place have essentially disappeared. And we suspect this is significant in terms of helping confine the effects of supernova feedback, which at earlier times could easily disrupt the central galaxy. So this kind of pressure fluctuations effect is kind of one important effect we've identified, kind of with respect to the role of the CGM in galaxy evolution. Here are just couple other images from the simulation to kind of illustrate the outside-in character of CGM virializations in the cosmological simulation. So now these images are all at redshift of 0, but I've selected two different galaxies. The one at the bottom is the same as on the previous slide, but the panel on the left kind of zooms out a little bit, and so you can see how the hot gas extends out to at least the virial radius. But the top panel here is new, and it's a lower mass galaxy, which by Z of 0 has not yet completed the virialization of its CGM. And so what you can see when you plot the gas all the way to the virial radius is that that volume is mostly filled with hot gas, but the inner parts are not yet. So the inner 0.2 to 0.3 virial radii are still cold and have not yet virialized. And so this is a case where the CGM looks like this, and again, you don't yet have a stable thin disk inside. Okay. And so what I'll do next is present some evidence that the time at which the inner CGM virializes coincides quite accurately in time with the changes in central galaxy properties that I've been mentioning. And the first column is again one single example. The top panel is star formation rate as a function of time. And you can see other magnitude fluctuations in that. Those other magnitude fluctuations stop roughly here, and the star formation rate becomes more time steady. And this dotted vertical line that is plotted in each of the columns that I will show is actually not tied to this top panel. It's entirely based on this bottom panel here, which is a indicator of whether the CGM is virialized or not. So T equal over T free fall at the 10th of the virial radius. When this value crosses a threshold of order unity is when we say that the inner CGM has virialized. And we see that this corresponds quite accurately in time with when the star formation rate became more stable. And in the middle panel, we see the effect that it has had on flows of gas in the CGM. So this is the mass outflow rate of gas at the 10th of the virial radius. So positive values correspond to outflows, negative values to inflows. And you can see that at early times you have these large kind of cycles of inflows, outflows. And these cycles stop rather abruptly around the time of inner CGM virializations. And in particular, you no longer have these regular, very powerful outflows, but rather you settle into what is mostly a slowly cooling halo of gas that falls onto the central galaxy. And the two other columns here are semi-randomly selected other simulated galaxy. And here this is to kind of give you a visual impression of how in each case the time which is identified as when the inner CGM virializes corresponds pretty accurately to the time when the outflows became suppressed and the star formation rate stabilized. Okay, a little bit more statistical are these panels here. So this is now from a set of about a dozen simulated galaxies. There are way more than 12 points on these diagrams because for each simulation we have multiple snapshots. So what the left shows here is, again, a measure of star formation rate variability, and then plotted as a function of T cool over T free fall in the inner CGM. And again, what you can see is statistically, prior to inner CGM virialization, you have order of magnitude type fluctuations in the star formation rate, and these drop rather abruptly around the time the inner CGM virializes. And on the right-hand side, we have a measure of rotational support. So this is V over sigma for the gas. Again, at early times, statistically, these values are small about the unity, maybe 1, 2, 2, or 3. And then these start increasing fairly quickly at virialization of the inner CGM. So this is evidence that the emergence of kind of high values of V over sigma correlates in time with virialization of the inner CGM. Okay, so far I've talked to you about this kind of pressure fluctuation effect. There is another effect that we have identified with respect to CGM physics that appears to play a role in the formation of thin disk galaxies. And this is the fact that the way that the gas accretes through the CGM and onto the central galaxy has a big effect on how angular momentum is delivered to the central parts of the halo. And here the idea is that when gas falls in from large-scale structure and is still at, say, a virial radius, it has a wide distribution of specific angular momentum. So this is a result from the cosmological simulation. That result, you can see it in the width of this gray band here. So what this shows is the width of the distribution of the cosine of the angle between the angular momentum of accreting gas and the angular momentum of the central galaxy. And here the horizontal axis is time as a relative to the time when the gas is going to accrete onto the central galaxy. So on the left, you see times well before the gas reaches the central galaxy. And at T of 0 is when the gas reaches the central galaxy. And what you can see in this example in which the gas accretes predominantly cold is that the wide distribution of specific angular momentum that we have at large radii remains wide all the way to the time that the gas crashes into the center of the halo. And I think this is because when your gas comes in the form of cold clumps and filaments, these cold clumps and filaments effectively don't talk to each other before they meet at the center. And so the gas gets to the center in a kind of a complicated geometry, and that's when stars first form out of that cold gas. And so we find empirically in the simulations that the stellar distributions you get in this regime tend to be irregular like this one, or at least geometrically quite thick. Okay, and then the other limit is the limit in which you have more like a cooling flow accretion process. And there the difference, I think, is that in hot gas, specific angular momentum differences can equalize through pressure waves that propagate in the hot medium. And that occurs in a sound crossing time. Okay? And in a virialized halo, essentially by definition, the sound crossing time is of order the free fall time. And in kind of the slowly cooling gas limit we're talking about, the accretion time is a cooling time which is much longer than either the free fall time or the sound crossing time. And so what this means is that in this limit, there's enough time for sound waves in the halo to equalize angular momentum differences before the gas gets to the center and accretes onto the central galaxy. And the quantitative signature of this is the narrowing of this specific angular momentum distribution from one which is wide at large radii to one that becomes narrower and narrower until it is indeed quite narrow before it reaches the central galaxy. And so what we think happened is, because of this kind of equalization of angular momentum differences before you reach the central galaxy, is that you form a thin gaseous disk before the first stars form out of the gas configuration. And so you first form the stars in a thin gaseous disk, and then on top of that, you have this hot gas that is kind of confining the supernovae that subsequently explode and which at earlier times kept disrupting the forming galaxy. Okay, just to put all of this together, there is a cartoon picture of how we are thinking about the role of CGM virialization on the formation of thin disk galaxies. So at high redshift or in low mass dark matter halos, and it's probably mass, which is the primary parameter here, you have clumpy free fall accretion of cold gas. These cold gas clumps reach the center of the halo with a wide distribution of specific angular momentum and kind of a chaotic, geometrically thick configuration. And so you first form stars in a disturbed morphology, and then you have bursts of stellar feedback that easily ejects the remaining gas out to large radii into the CGM, drives what you might observe as galactic winds, and kind of keep preventing the formation of a long-lived disk. And then eventually your halo becomes sufficiently massive that the gas inside it has fully virialized. From that point on, you get smooth accretion of cooling gas in the cooling flow type model, and you have coherent angular momentum deposition in the inner regions in a subsonic accretion flow. And so your stars first form in the disk, and then when the supernovae explode, they do so in an environment which is kind of highly pressurized and with no paths of least resistance for large-scale outflows to be easily launched out to large radii. So this is a set of physical hypotheses. I think they are reasonably well supported by the simulation data, but I'm looking forward to continuing to test this picture in more detail. I'll put my summary slide. Oops. There's a bit of a delay with the slide changer, you may have noticed. Oops. Okay, thank you.
Okay, thank you. We have time for questions.
Thanks for a wonderful talk. Two related questions. One is technical. When you talk about the cooling to free fall time at a given radius, how is that cooling time determined? Is it based on the, at that moment, properties, instantaneous properties of the gas? Or is it based on the past history of the gas?
Yeah, so the way you do this does matter a little bit. And so really the question we're trying to ask is, if the gas were kind of shocked to the virial temperature, how long would it take it to cool? So actually, this is probably something we should talk about more, maybe offline. But the temperature we use is actually like the virial temperature. And we use kind of we have a pressure way of kind of inferring the effective density you have to plug in this cooling time. So yeah, so it is the cooling time if the gas kind of had shocked at that radius. And it tells you whether a virialized phase can survive or not. But it's not necessarily the local cooling time of the gas, which varies from place to place in a multi-phase medium. Yeah.
And the other question was, I'm intrigued by the transonic phase.
Yeah.
Is it true that the transonic phase only lasts for about a free fall time, or does it last for a longer time? I think related to that is that cold gas that you see around the central galaxies, that gas that just came from the outer halo cooled and it's still on infall, or is it gas that already has cycled through the galaxy and is being pushed out and there's some pressure that makes that transonic phase last for longer than the free fall time?
So let me answer the first part of the question. I'm not sure I understood the second part. And I'm not sure this is what you're asking. But one question you might ask is this configuration, is this something that happens in the real universe? Is it stable? And it surprised me, but I believe it is stable. In a 3D simulation, when you keep kind of feeding gas on the outside, you have this long-lived sonic point. So it can stay, so long as you feed gas from the outside and kind of you maintain the same kind of density of inflow, it stays there essentially forever. Yeah. So it's not like something that like dynamically collapses on itself.
That answers the question.
Yeah. Okay.
So, in the local universe, we have